Okay, so well, this talk is prepared to be shorter than the other ones, and it's unfortunately a talk of mathematics. So, but Professor Kvitanovic put an interesting title, "Terrible Allergies Due to Pollen," to see if someone would come. Okay, so let's. It's this related to the problem that I am working for my thesis.
Mikel, either speak louder or be closer to the Justin Bieber microphone.
To which one? But it's not. This is for the recording, and this is for here. Okay, so now is easier to hear.
That's much better.
Good. So well, we will present many definitions. Okay. So you have X is the manifold of your dynamical system, and it has a probability measure, and there is a function that goes from X to X, and it preserves the probability. So this is an object that we have encountered a lot in this course. Now, consider also a function A that goes from the manifold to the linear group in d dimensions. Okay, so this is the group of d-dimensional matrices that are invertible. It is a group. And assume that the map is a Borel map. Assume that it's measurable. So in the theory of dynamical systems, these objects that are called linear cocycles are very important. So these are functions that go from the manifold times Rd to itself, okay? And the system is defined, so for any point x, v in the product, so you take a point in the manifold and v a vector, you send it to f of x, where f is the measurable transformation, and v, you multiply it by the matrix A of x times v. So the dynamics in this coordinate is the dynamics of f, but the dynamics in this coordinate is kind of twisted by the dynamics by the map A. Okay, so it is called a linear cocycle. And just a quick observation is that if the composition of this system n times is just fnx. Of course, this dynamics is the same as the dynamics of f, so it just appears n. But here is anx, where anx has this composition. All right. So let's give three examples. The first two examples are mathematical in nature. So in the first example, we're going to think of the manifold with the transformation f as a random process. So typically a Bernoulli scheme. And so this expression, the expression that we had for an before, for the composition of the right-hand side, this is the an. The an has to be thought as a random walk, because to x you apply f, then f switches f randomly, then you take a, and then you do these multiplications. So you think of this process indexed by n as a random walk. Okay? So this interpretation is very important in passage percolation, in first passage percolation, and there is an important theorem that states that almost surely in X there is a well-defined limit velocity of the random walk. All right? Yes?
Is I'm still trying to understand. Is A a push forward of this vector that's based at X? Or,
sorry? Which vector based at X?
So if you go a slide back.
Yeah, so there is here, everything is in a linear group, etc. So there is, talking about push forwards, etc. is not so interesting. But yes, so here what?
Okay. So, so here you have a point, x, based on your manifold.
In the manifold.
And then your
to x,
this,
exactly. To x, there corresponds a matrix.
Okay, so is A, okay, so A of X is a sort of map induced by F.
No, not by F, by A. It's not related. It's, you see, here F comes into play because this A acts on this X, and this X depends on F, right? It's like it's still difficult to understand in the beginning, right? But the A is a map that doesn't depend on F. But f comes into play in the right-hand side because x comes from f here.
I see.
Okay? So it's a bit complicated. Yeah, thank you for... And no, there is no question about I mean, all these manifolds are as simple as possible. So, okay. So now, yes?
You can continue. I'll
Okay.
turn on the other computer.
Okay. The second example is the derivative cocycle. So in the derivative cocycle, a of x is the derivative of f at x, where f is some diffeomorphism. So we have seen this a lot in this course. So if some transformation, you take the derivative, and a of x is the derivative of f, whenever the derivative of f is invertible. All right? So, well, then there is an interesting theorem that we proved last time in a seminar for mathematicians that says something very interesting, but let's not talk about it now. Okay, and the last example that I want to talk about is the Schrödinger Cocycle. So in the Schrödinger Cocycle, the manifold is the d-dimensional torus. So is everyone here clear about the d-dimensional torus? So for instance, in one dimension, the d-dimensional torus is just a circle, right? In two dimensions, the two-dimensional torus is the surface of the donut. And in 3 dimensions, it's whatever, no? It's some manifold, no, the way they explain it's a manifold that if I go in this direction, and then suddenly I translate myself here, no? And so on. So in the Schrödinger Cocycle, you have TD, you have the Lebesgue measure, and you have a translation in the torus, no? So the translation of the torus is something like this, no? You are translating yourself in this. And the Schrödinger Cocycle is a map from TD to the special linear group in 2 dimensions that is like this. And let me explain why it is like that, if I have some time. This very interesting cocycle. So the cocycle comes because of the following. The physical motivation is given by a very, very simple process. It's just take a line, and in the line you put you imagine, so the line is indexed by the integers in the line, okay? And so you drop a particle. So I don't know anything about quantum mechanics, but what they say, is that the system is characterized by the following. You say that the probability that the particle is in some subset of the integers is the sum of some element of psi n, where psi belongs to the space L2 of z. Well, L2 of z, of course, is the set of sequences that are summable, okay? Which is what you have here, okay? This is a complex number. Now, the evolution of the system has to obey the Schrödinger equation, where H is this interesting Schrödinger operator, where the probability distribution of the next particle, of the next vecino, of the next neighbor and the previous neighbor is involved. And Vn is a potential. So the cocycle that appeared previously in the previous slides comes because the study of this system is often reduced to the study of the eigenvalues of this this operator on sequences, all right? And this equation is equivalent, by a trick that we have used in this course as well, to solutions of this system, where TEN is this matrix, and this is exactly the matrix that appeared in the previous slide. All right? So, a very particular case that is very important for mathematicians is the almost Mathieu operator. In that case, the torus is one-dimensional and the potential is as simple as possible without being trivial. So you just put one Fourier node, okay, and that's it. So in that case, the Schrödinger operator is called the almost Mathieu operator. A problem that people from mathematical physics gave mathematicians, specifically dynamical system people, was that based on the numeric, the shape of the spectrum was conjectured to be a Cantor set. So Cantor set is a nowhere dense set. Okay, so you take the closure of the set, and that closure has empty interior. And they wanted to see this for some reason. And so Mark Kac in 1981 offered 10 martinis for the solution of the problem, okay? And so mathematicians started working this like crazy. And actually this was solved in 2009 by Artur Avila, which is a mathematician who will probably earn the Field Medal this year. So, well, in the particular, this was like I will finish soon, but I just want to say that we are not interested in the spectrum of the operator, but what we are interested is in the dynamical properties of the cocycle. In particular, we're interested in two concepts that are related to conjugations of the dynamical system generated by the cocycle. Okay, so one is reducibility and one is almost reducibility. Reducibility is very strong. You make a change of variable in the cocycle and you convert the cocycle into a constant matrix, and in almost reducible is something much weaker. Okay, so I don't have time to explain these two particular notions. They are difficult, they are complicated to understand, but let me just say that in the case of Schrödinger cocycles, results have been obtained in these two cases by Eliasson. So well, and there are some pictures about in the case of fibered maps. This is just so that you have some idea. So in this case, the system that is being studied this is a very simple system. Okay, so you have a rotation of the torus. So you have z theta goes to az plus c squared times 1 plus cosine theta plus omega. All right, so it's not a cocycle because you don't have you can think of it as a cocycle into GL1. In that case, the orbits that are useful to study, when you iterate them for large n, you get this object that we have not found in this course, but we have mentioned it, that is an invariant torus. Okay, so these are the first few iterates, and then the orbits converge to this invariant torus, okay, around the origin. And the set of points that have these dynamics this is a three-dimensional set, okay, in the torus. And so it is these points that are here graphed. The points outside, when you iterate them, they go to infinity. So the dynamics that you want to study is in this set. That is kind of complicated, but it also has some structure, as you can see. And well, this is just if you cut this strange thing in the middle, you get this set. Right, so it has some fractal structure, but very little is known. So for physicists, if any of you is interested in the almost Mathieu operator on the concepts of reducibility or almost reducibility, for Schrödinger operators or for any kind of cocycle, and if you know about GPU programming, then it's we mathematicians are very interested in those concepts. Okay, and well, so I will finish now and see if you have anything to say or any question. Yeah, it's time. Thank you.
We have 2 minutes for questions.
Why GPU programming?
Because the algorithm to compute this set that we had in the end, that is a set where we restrict ourselves to study the interesting dynamic, is a very simple algorithm. It just has to compose some very simple function 1 million times. So very simple. So it seems that for GPUs this is particularly good because you have a simple algorithm that you can iterate many times over many little processing units. No? So this would be useful for reducing the time of the program. No, it's a programming question about why the GPUs. No, so he was asking why GPUs are useful for this. So yes, it was a programming question. But yes, it will reduce the time of the study of the things by a lot. Okay. Yeah. Okay, so if there are no further questions,
We were able to find a stable torus, invariant torus.
yes,
for this map.
yes. Yeah, there are many invariant torus, yes. It's not difficult to find them. Around the origin, there are many, yes.
So if it was unstable, could you find it?
Well, in this case, we don't have that particular thing. But certainly, this question of almost reducibility is based on this. Yes, you can find them. You can find them, and mathematically there is an algorithm to find them. Yes, yes, yes. Yeah. Okay.
Thank you. You can just take it. All right. Building some experience.